Hello, Marx here. This is a brief thing about centripetal forces. Since we need that in the current chapter. We will look at this deeper further on, but first I will just we will derive a formula how to calculate the force given the velocity and radius of a circular path. So what we have here is something that moves in a circular path around. With the radius r of the circular path, and the speed is kept constant. Let's say this is v there. The thing is that the direction of this will change as it rotates about. And by the way, hello cat. Should you have say hello to the audience? Hello. Yay. Okay, back to the centripetal forces. So we still have the same speed, but a different velocity. These are 90 degrees, right? They're always moving 90 degrees to the radius. And basically, if I take these two, let's call this V1 and V2, and put them like this little part, they should be equally long, technically speaking. V1, V2, this little thing here is a change of velocity. And if we look at this for a very, very short time, this is basically 90 degrees, but that will also basically be 90 degrees, but it doesn't really matter. And this is some angle theta there, and this should be the same angle theta, right? Since this is a 90 degree turn and this is a 90 degree turn. If we now take and say this is also equal to v, right? That is the speed, that is the same. And we also know that acceleration is change of velocity over change of time. So that is what we will deal with. We will look at how big this change of velocity is. And because we will have an acceleration, if we change our velocity, we will have an acceleration, in this case an acceleration inwards all the time, which also means that we must have a force directed inwards at any point. This force could be supplied by, for example, a rope, the gravity, an electrical field, or anything else that pushes inwards all the way around, right? That is what we call the centripetal force. Okay, so if we look at this, we can see that this triangle is similar to this. So that means that the change of velocity over the velocity, so this over that, must be equal to this length that we say we call this delta S over r. We can now multiply both sides by v to get that a change of velocity equals to delta S over r times v, and I will write that as delta S times v over r. Next thing we do is we will divide by delta t the time it takes to move this distance to get an acceleration, right? So our acceleration will be the change of velocity over the change of time, and that will be, we'll divide this by delta t, so I can do that over here, right? But this thing here, delta S over delta t, is nothing but the velocity, or the speed rather, of the thing going about in an orbit. So this will be v times v over r, which will become v square over r. So we have this important formula that acceleration in the circular motion is acceleration is v square over r. Or if we, since we have force is mass times acceleration, if we multiply this by the mass, we get this formula for the centripetal force: mass times v square over r. And that is indeed an important formula that we'll use many times. So we can see here that the force required to keep you in a circular orbit increase extremely strongly with the velocity. It also depends on the radius. The shorter radius, you have a bigger force, but definitely the velocities here is the key thing on how big the force will be. And the force will then be inwards, acting on the object, and the object itself will try to continue in a straight line, right, by Newton's first law, and that will must be counteracted with the force inward. What we call the centrifugal force is if you would be, for example, in a rotating drum or something, and you will be pressed against a wall, you will feel kind of a force pushing you outwards, but actually it's the wall pushing in towards you and you change the direction. The centrifugal force is therefore a fictitious force. It doesn't really exist. It's a centripetal force that you have here, but you will experience it as a force. So think about this: the wall is here, you are here, and the wall is moving around in a circle, pushing it against you. That is the same thing if you're in a car. You turn around a corner, then what happens here is that you will feel like you're pressed against the door in the car, say, but what happens is that you will try to continue in the straight line whilst the car is moving in towards you. The centripetal force here is provided by the friction between the tires and the ground, and the centrifugal force is the fictitious force you feel that pushes you into the wall, but actually it's the wall that comes against you, right? Anyhow, that is a bit about centripetal forces. We'll use that in the next session. Thank you.